I now wish to turn to a different subject, that of intermolecular forces. In order for a liquid to vaporize, which means to turn from a liquid into a gas, the forces that hold together its individual molecules in the liquid form have to be overcome. If the molecules are held together by really strong forces, a lot of energy will be required to pull them away from each other, and the compound will therefore have a higher boiling point. This brings us to a wonderful question. Sort the following molecules in order from highest to lowest boiling point and explain why. Now, I'm not going to do this, but I'll let you attempt it on your own. I now want to move to a different subject, drawing chair structures. Now, I know what you're thinking. What in the world does that mean? Cyclohexane rings are very special because they're found in numerous real-world organic compounds. Cyclohexane rings typically adopt a three-dimensional shape that we call a chair conformation, which is shown here. So if we look at cyclohexane, which we can draw as a simple line bond structure shown here, we can acknowledge that if we drew out every one of its attached hydrogen atoms, it would actually look like this. That's a lot of hydrogen atoms. Now, what I want to tell you is this. If we were to actually build a real three-dimensional model of cyclohexane using an organic chemistry model kit, for example, and you were to tilt that model on its side and look at it from the right angle, it would look something like this. Cyclohexanes are shaped like this structure three-dimensionally because being shaped that way allows the bond angles around each and every one of the sp3 hybridized carbon in this ring to be around 109.5 degrees. Now, this type of structure drawn right here is called a chair structure or a chair conformation. Cyclohexanes adopt this shape because, once again, doing so allows each of their bonds to have very close to the ideal tetrahedral bond angle of 109.5 degrees. And why in the world do we care? The reason is because cyclohexane and cyclohexane-like molecules are so common in nature, especially when we start talking about sugars and their polymers, that learning how to draw and interpret these chair conformations is extremely important. Now, one mistake I see rookie students frequently making when they draw chair conformations is doing it in an extremely hideous way, a way that makes us more experienced organic chemists want to cry and vomit in disgust. So I want to teach you how to do it right. You start by drawing two lines like this. Now, these two lines are supposed to be parallel to each other. The closer to being parallel they are, the better. Now, I'm not going to be extremely uptight and brutalize all of you, my students, if you don't do it perfectly. However, if you make them look so unparalleled that your chair conformations appear like a 5-year-old drew them, I will totally dock points from your assignments and tests, unless you happen to actually be 5-year-old. Like one of those crazy 5-year-old genius kids who's taking college classes. If you were one of those, I'd probably cut you a little bit slack. Anyway, where were we? Oh yeah, so you draw these two lines, and after you do that, you draw two more like this, which also are supposed to be parallel to each other. Now you draw two more like this, which are also once again supposed to be parallel to each other. Now you'll notice that I've color-coded the bonds that are shown here that are supposed to be parallel to each other so that you can keep them straight. Congratulations, you've now drawn a correct chair conformation of cyclohexane. You deserve a party. Now, one more thing that I need to point out is that you will need to gain the ability to draw both types of chairs, the one that I've shown here and its mirror image, which is shown here. Because chair structures often look like bow ties, they're kind of crooked, I often call this the mirror image bow tie of this. I now need to teach you a little bit of terminology. As you saw in our earlier slide, each of the appendages, or substituents, attached to the carbons in our chair conformation have the shape and angles shown here. Now, one thing you need to understand is this. The hydrogen atoms that are pointing straight up and down in this figure, which are pictured in pink here, are called the axial hydrogens. The hydrogen atoms that are pointing kind of diagonally, slightly up or down, and are pictured here in green, are called equatorial hydrogens. The word equatorial, incidentally, stems from the same root as the word equator, which is the horizontal latitudinal line that bisects the midsection of the Earth. Just for you geography majors. Now, it is noteworthy to remember that generally speaking, the equatorial positions are more stable. I'll explain why in a few moments. With that said, I now want to teach you to correctly draw your axial bonds. To do this, you should look at each atom in your chair conformation and ask yourself, if this atom were an arrow, which direction is it pointing? If it's pointing up, then the axial bond connected to that specific atom needs to point directly straight up. If it's pointing down, then the axial bond attached to that specific atom needs to point straight down. I'll now show you how to do this. Let's go around the circle and start with the upper right-hand corner. I don't know why I always like that one. If you were imagining if this were an arrow, which direction is it pointing? Well, it's pointing up. So what that means is that the axial atom and bond that is attached to this atom has to be pointing directly straight up, like this. Let's go over here to this next atom in this ring. If this were an arrow, which direction would it be pointing? Well, it kind of looks like it's pointing down. So I would go ahead and draw my axial bond coming off of that atom pointing down. Now we can continue this form of logic all the way around. This atom is pointing slightly up, so the axial bond at that position needs to point up. The atom down here in the lower left-hand corner is pointing down, so the axial needs to point down. This one in the upper left-hand corner is pointing up, so the axial one needs to point up. This last one right here is very interesting. It's supposed to be three-dimensionally located behind all of these bonds that are in the front. So when we draw the axial bond, which of course is going to point down, we often show it dashed or broken here. Now that doesn't imply that it's actually a broken bond. What it implies is that in three-dimensional terms, this bond is in front of the pink bond that's shown back here. And now to drawing the equatorial bonds. It's a little trickier, but it becomes slightly easier if you've already drawn your axial bonds first, which is why I did that. At each atom in the chair, we should ask ourselves, which way does the axial bond that's attached to this atom point? Does it point up or down? If it points up, then the equatorial bond that's attached to that same atom should point at a roughly 109.5 degree slant down. Now, if the axial bond at that position points down, then the equatorial bond that's coming off of that same atom should be pointing roughly at a 109.5 degree angle up. I'll show you now how to do this. Let's start once again with our upper right-hand corner bond. I look at this atom and I ask myself, which direction is its axial bond pointing? You'll notice that it's pointing up. That means that the equatorial, which is coming off of this atom, should be pointing down roughly at a 109.5 degree angle relative to the axial at that same position. Let's look at this atom. Which direction is its axial bond pointing? It's pointing down. Hence, the equatorial bond coming off of this atom should be pointing up at an angle of about 109.5 degrees relative to the axial at that same position. We can continue doing that all the way around. Each of these equatorials should be parallel to the corresponding bonds located inside the chair that have the same color. One thing that frustrates organic chemistry professors to no end is when they see equatorial bonds, such as this pink one right here, being drawn at a completely incorrect angle. If it were pointing up, for example, that would be very, very wrong, and I would definitely mark it wrong if I saw it on an exam. So now we have our chair. Now, as I mentioned, the bonds that are pointing straight up or straight down are the axial bonds, and the bonds that are extending at slight angles out, away from the center of the ring, are called equatorial bonds. Those are shown pictorially and colorfully here. Now, also, as I mentioned earlier, the equatorial bonds are generally the more stable place to be, especially for large-sized substituents. Why? Well, the reason is because the axial positions actually place the atoms at the ends of them three-dimensionally closer to each other than the equatorial positions. Now, as we learned back in general chemistry, atoms like to be as far apart from each other as possible. So if you're talking about a large tert-butyl group, for example, you don't want to be stuck in an axial position because you'll have to be staring at each of the other three axial substituents much more closely than you would be if you're occupying an equatorial position. Now, this type of disfavorable interaction between axial substituents, which can occur with the axial substituents pointing up as well as the ones that are pointing down, is called a 1,3 diaxial interaction. And it kind of sucks. Well, at least for larger sized appendages. Hydrogens are small enough that they can actually handle it quite well.